Today we're going to be looking at an example for neutral heat transport between two plates. So first we go to New and from Example, and we're in the Plasma Discharges section today, Other PD, and down to Neutral Heat Transport. And we can see what this simulation is the heat transport between two plates, one at 1000 Kelvin, the other at 250 Kelvin, with a neutral argon gas in the space between. So we choose, we can save this, and it will load the simulation. Here we are with our simulation setup. You can see we have just a two-dimensional grid. And if we go to description here, it kind of tells us a little bit about what we're going to be doing. For this simulation, as I said, it's the heat transport between two parallel plates, one hot, one cold. So we have to set up some information about these plates. They're already set up in the example. These constants will always be here down to our argon mass, which we put in ourselves. The pressure is important here. Put it at 0.2, but this is a parameter that the user can change and will result in different interesting physics. So we'll come back to that in a bit. We set the temperature of the hot plate to 1000 Kelvin, the temperature of the cold plate to 250 Kelvin. These constants here, dref, tref, nu, have to do with the cross-section of the interaction between the argons, so we'll come back to that later. But we have two distance parameters. We have the length of our grid, which is the x direction here, and we're going to separate them by 1 meter. And then the width, and this tunable parameter if you want, but I've set it to 0.2. Based on these constants that we set, we can then calculate some other important physical parameters, things like the temperature of the argon, and here we can put in expressions like square root hot temp times cold temp. So this is kind of going to be the equilibrium temperature of the argon after it interacts with the hot and cold plates. We can calculate things like density, the mean free path. This is important for us because we want to make sure that we're resolving the mean free path with our grid spacing, and that's done automatically in here. You can see the dx is our grid spacing, and it is a function of the mean free path. We're making sure that we have at least two mean free paths, which is the average distance a particle will go before interacting. We want to make sure we have two of those in every grid spacing. And this just ensures that we have enough collisions occurring in each cell to get good statistics. We automatically calculate things like the number of cells based on this dx and so on. We can see if I come back here and I change the pressure, let's say I increase the pressure to 0.3, what we would expect is that at a higher pressure we have higher densities for a given temperature. So our particles are closer to each other, they're more likely to interact, and so our mean free path is going to go down. That means the distance that the particle goes before interacting will go down. So our grid spacing also needs to go down to accommodate for this, and we can see that happens automatically as I change the pressure. I get higher resolution if I go to higher pressure, and if I go to lower pressure, I get lower resolution. So this is set up to make sure the physics will be correct regardless of the pressure you put in. Right, so going on to basic settings, we've set our time step, dt, and this we set in the parameters tab, which is basically just to make sure that particle moving at the temperature from the hot plate, the thermal velocity associated with the temperature at the hot plate will not cross more than one cell in a single time step. So we set that in the basic settings here, our dt parameter. We've set it to 15,000. I'm going to change this to 4,000 just because we don't need to run for 15,000 to get equilibrium, and you'll see that when we actually run the simulation. A lot of these are kind of standard settings. We've changed the dimensionality to 2. This could be done in a 3D simulation, and you would get the same result, but it's faster in 2D. We're uniform grid. We've set it to no field solver. This is a DSMC simulation, direct simulation Monte Carlo, so we do not need any field solves. These are neutral argon atoms, so we have no potentials, no electric fields. This is pure DSMC. We've set periodic in Y, which is the direction parallel to the plates, perpendicular to the plates, between the plates. We don't have periodic. We have special boundary conditions, which we'll get to. For the particles, we are including particles. Obviously, we need argon. And we are including reactions. Here we have a few options. This reactions framework is the fastest, most flexible, so we're choosing that one. And there's various settings you can choose for these. But let's go on to the grid. This is where I've set the size of the grid. So we had those parameters, xmin, xmax, ymin, ymax. Those are calculated back in the parameter section here. So xmin is just the length over 2. So we're starting at negative 0.5 here and going to positive 0.5. And then we set our number of grid points, and this is what constructs the actual grid that we see. For particles, I needed to add argons. So to do that, I can just right-click on kinetic particles and add neutral particles. I've already done this, so the argons are here. When I click on argon, I can see I have density I can provide. I can say whether they're relativistic or not. In this case, they're not relativistic, so I can choose that, and it will reduce some of the computational complexity. We have consonant weights. This is something you could change, and this might be a simulation where managed weights or variable weights are something useful, but for now we'll do constant weights. I'm saying I want 100 macroparticles per cell. This is to make sure we have good statistics. This could be lower if you wanted to use variable weight. Since we're using constant weights, we need it to be relatively high to get the correct answer. The molecule we're using here is argon. You can choose different species, and you'll get the mass and ionization energies provided for you automatically. We're using argon. So we have created these particles, argon, but we need to then load them. So just creating them doesn't make them show up in the simulation. We need to say, all right, where are they going to show up? So I can right click on those and I can add things like loaders. I can add particle boundary conditions. I can add neutral emitters. We've added a loader, and in the loader we've said, all right, well, I know I specified already I want 100 macroparticles per cell. So I'm going to do 10 by 10. For a 2D simulation, gives us 100 particles per cell in the load. I have specified a thermal distribution for our argon, and here that is a space-time function that I created up here in this space-time function section. So we can see all this is a Gaussian with a sigma of the thermal velocity and a mean of 0. And the thermal velocity is a parameter that we computed up here. So it's just standard expression for thermal velocity. We also need special boundary conditions for these argons because they're going to hit the hot plate and they should gain a energy that puts them at roughly the temperature of the hot plate, and vice versa. When they hit the cold plate, they're going to lose energy to that cold plate, and they should come away with some velocity corresponding to the thermal velocity of the cold plate. In our argon boundary condition, I've added this boundary diffuse reflector, and that's what these hot and cold plates are, boundary diffuse reflector. We don't want to give them any net velocity, but we do want to give them a thermal velocity corresponding to the hot thermal velocity of argon that's at 1000 Kelvin, and then a cold thermal velocity for argons that's at 250 Kelvin. Doing this means that our argons will start off at 500 Kelvin. You can see the initial argon temperature is 500. We'll have these argons bouncing around, hitting the plates, exchanging energy with the plates, and that will change this total energy or temperature of the argon. And near the hot plate, it should be hot, and near the cold plate, it should be cold. And we'll have this heat flux going from the hot plate to the cold plate. And that's what we can actually calculate theoretically for this situation, and it's what we're going to compare to. The one last thing we need is this, for the physical simulation, is the actual collisions. If we didn't have collisions, the argons would just hit the hot plate, stream freely across the domain, hit the cold plate, exchange energy, and so on. And so that would give us some heat flux across, but that's not necessarily the physical heat flux. If we have high enough collisionality, i.e. our pressure is high enough that these particles are close together, they want to hit each other, then our heat flux will change. And so to get that accurate, we need to include this elastic collision. So here I have kinetic particles that are argons, so I'm going to choose particle-particle collisions. I can add a collision type, and I have all these to choose from. I've chosen elastic, and then we choose the argons as the A and B in the elastic collision here. We can choose our cross-section type, and this is where those cross-section values that I referred to earlier come in. We've taken these from Bird's book from 1994, which says that the argon has some reference diameter in meters, has some reference temperature, and we're using 0.5 for the nu, which is the exponent for the power law cross-section. And this is the variable hard sphere model proposed by Bird. So this cross-section coefficient we can calculate based on the equation from his book, which gives us some value that we use down in the actual cross-section here. So the coefficient is this parameter, and then the exponent is minus 2 times nu. We know nu is 0.5, so this is minus 1. So this is saying that our cross-section variable is velocity. The sigma is inversely proportional to the velocity, so sigma v is just a constant, and that's what is used in the code for the collision. We're going to update this every other time step. This is essentially just to provide speed. We could do this every time step, and we'd have less occurring every time step. And that's just an option that one can play with. Right, so that's all the physics we need. But we also then need to be able to tell if we got the right answer. So we're going to add some histories. And these histories allow us to record information that we're interested in. In this case, we want to know what the heat flux is across the argon from the hot plate to the cold plate. So we can add a history. In this case, it's a particle history because we're wondering about particles interacting with the boundaries. And we can go down to this particle energy exchange or change from the boundary. We've done that twice here, this energy from hot plate. And all we do is select that boundary absorber we made before, the hot plate. And again, for the cold, we can do the cold plate. For this average here, I've selected a combo history, binary combination. And this is essentially just averaging the two heat fluxes together. I have 0.5, 0.5, and we're adding. This is a negative 0.5 because these energies will have opposite signs, because one of them is giving energy to the particles, the other one is taking energy from the particles. So if we want an actual average, this coefficient needs to be negative. I've also added a couple histories, like calculating the number of argons throughout the simulation and the argon energy throughout the simulation. These aren't necessary, but they can shed some light on whether the simulation is acting correctly, and I'll show you that when we get to visualize. So we have our simulation set up. Now we want to run it. So we must save and set up here. That generates the in file, which we can look at if we want, and has what the code actually sees. Then we go to run.